Bismillahirrahmanirrahim. Welcome to lecture number 4 of the series of lecture on advanced computer architecture. In the previous 3 lectures, we have been talking about the computer design cycle, where we discussed what are the basic steps which we have to take in order to design a computing system. Then we discussed the quantitative principles which are based on the performance measurement of the microprocessor and the input-output devices. Then we made a detailed discussion on the performance and the price constraints in the design of a computing system. And then we concluded this discussion on the qualitative principles by talking about what are the benchmarks which are used for the design of a complete system, including the microprocessor and the input-output systems. So with this much introduction about the computer system design, today we will be talking about what is the basic concept of instruction set architecture, which is in fact having a pivotal role in the design of a computing system. The computing system in fact can be defined by 3 basic pillars of the computing system, namely the hardware, the software, and the instruction set. Hardware deals with those parts of the computing system which have got physical design of the system, whereas the software deals with the basic features of the programs which are being used to run a particular application. However, in all these, both in the design of the computer hardware as well as the software, the role of the instruction set architecture is pivotal. However, in fact, from the era of 1950 to 1960, the computer architecture course was considered as a course on computer arithmetics, logic design, and study of and design of different techniques in order to solve the arithmetic problems. Then in 1970 to 1980, the emphasis has been on the design of the instruction set, which is basically partitioning the design of hardware and design of the software. However, instruction set is a portion of the computer which is visible to the programmer. Then up till now, in fact, the computer architecture is taking into consideration all the attributes which are necessary to design a computing system, and then based on the quantitative principles of the architecture and the design, we made a price performance analysis, and price performance systems are being studied. So this is what is the basic background of computer architecture. Whereas, what is an instruction set architecture? Now I will talk about the instruction set architecture is basically an interface between hardware and software. It plays a pivotal role in understanding the computer architecture from both the design perspectives and the use perspective. However, the design of the hardware and the software cannot be initiated without defining the instruction set architecture. Therefore, for a computer designer, the basic thing is that we must first of all describe the instruction word format. We identify how the memory can be accessed, that is how we can specify the memory address, and then what are different techniques which can be used for the data manipulation and control operations. Considering all these things, we can in fact first of all define what is an interface. A good interface is one which lasts through many implementation, and it provides portability and compatibility. Whereas it also provides the convenience in functionality for higher level implementation, and it also permits an efficient implementation at the lower level. So these are the basic considerations which we must have in mind in order to design a good interface. With this much introduction about what is an interface and how instruction set architecture is acting like an interface, I will be now talking about the taxonomy of the instruction set architecture. Instruction set design can be based on the hardware. For example, what is the basic design of the hardware, whether it is a stack-based design, or it is accumulator-based design, or it contains general-purpose registers. However, the design decisions are dependent upon number of attributes such as the technology, the machine organization, which particular programming language is to be used, the compiler technology which is to be used in order to deal with the software part of the system, and what is the operating system which is to be taken into consideration. So the basic differentiator is the storage type and what are the operands, how these operands can be stored in different types of these architectures. So based on this, we will be talking about the three major choices of the instruction set architecture. Firstly, we will be talking about the stack architecture. Then we will be talking about the accumulator architecture. And then we will be talking about the general purpose register architecture. The general purpose register architecture can be further divided into three distinct types. That is the register memory type, the register type, which is also known as the load store type of architecture, and the memory type of architecture. However, this memory type of architecture is presently obsolete. So the stack-based architecture is one where both the operands are implicitly on the top of the stack. If you look into this diagram, you can see that the address required in this type of architecture is 0, which means that the instruction always refers to the top of the stack. The operand may be either an input, which is shown in this diagram as a shaded orange type of block, or result from the arithmetic and logic unit may be placed in the next location on the stack, which is shown here in yellow color. Here both the operands are implicitly on the top of the stack, thus it is also referred to the zero address machine. Here the operand is placed either as an input or it may be coming from the arithmetic and logic unit. After the execution of the operation, the result is also stored in the stack. Therefore, both for the input purposes as well as for the output purposes, no address is required to refer to for the input or for the output. For example, here if we look into this execution of a small program, as you can see from this slide, where if we have to execute a higher level language instruction such as C is equal to A plus B, which requires an addition, and for addition the implicit operands are available onto the stack and they are placed by using the push instructions, and the push instruction, the instruction push A and instruction push B places the two operands onto the stack. The instruction add does not require any address for the operand to specify its location, because it is understood that it is a zero address instruction. Hence, both the operands will be obtained from the stack, and after the execution of the operation, the result will be placed onto the stack. And then if you want to place the result back onto the memory at a location called C, then we can use the pop instruction. So this way, the push and the pop instructions are only used just to transfer data into the stack or into the memory. Now we will talk about the accumulator architecture. Accumulator is a special purpose register within a CPU which is used both for the operands as well as to store the result on the completion of the operation. Therefore, the accumulator does not need any address if this is a single accumulator system. Therefore, in that case, it does not need any address. Whereas the second operand is assumed to be available in the memory, and it may be transferred or read directly from the memory with the help of instruction. For example, we can say that you can see into this diagram over here, in order to execute the instruction C is equal to A plus B, we assume that the A is already available onto the stack, B can be obtained from the memory. Therefore, the program will be written as load A. This means that the variable from location A will be transferred onto the accumulator. The add B instruction obtains the operand A from the accumulator, B from the memory, and it performs the operation. Then the result will be stored back into the accumulator, and from the accumulator, it is with the help of the store instruction, we can write it at a location called C. So these two, therefore, we can see that the number of instructions required in the case of zero address machine is 4, whereas the number of instructions required in case of accumulator type machine is 3. Now let us consider what is a general purpose register type of instruction set architecture. Basically, those architectures which are based onto the general purpose register, they assume that in the CPU there are a number of registers available, and these registers can be used for either to store the data, that is the operand, or to store the address of the memory. The relatively small number of bits of the instruction is needed to identify the register. We will now talk about the general purpose register architecture. You can see it from this slide that many general purpose registers are available in the CPU. Generally, the CPU register do not have dedicated functions. Rather, they can be used for variety of functions, such as to store the operands or to perform some addresses, to have some addresses or some control information also. Relatively small number of bits of the instructions are used in order to specify the name of the register wherefrom the data is to be obtained or where the result is to be stored. The general purpose register architecture has explicitly the operands available either in the register or in the memory or in both. So now let us see it from this next slide. As you can see that if we have to execute the same previous program, solve the expression that is C is equal to A plus B, the first operation will be that we will transfer the value from A location of the memory into the register R1. So this is done with the help of a load operation. The second operand may be assumed to be available in the memory at location B. Then the addition instruction can be written as add R3, R1, B. It means that we want to add the contents of register R1 to the contents of the memory at a location B and transfer the result into the register C. Then, in order to store the result at the location C, the instruction used is store R3, C, which means that whatsoever are the contents available in the register R3, store these values into the memory at location, namely C. So, this way we can use these general purpose registers, and the three different uses, as we discussed, talked about earlier, are we can use them either in the register mode or in the register memory mode. So let us first of all talk about the register mode. For the register mode, first we have to load both the operands A and operand B into the registers, into two different registers, say R1 and R2, by the instructions load R1, A and load R2, B. Whereas, then in order to use the instruction add is used in a register mode as R3, R1, R2. This means that add the contents of register R2 to the contents of register R1 and place the result into the register R3. This means that in this particular case, the memory is not accessed or the memory is not used. Whereas the second mode of operation is the register memory operation. The register memory operation is one where one of the operand is assumed to be in register and the other operand is assumed to be in the memory. And it is, for example, it is load R1A, which means that transfer the value of A into register R1, then add R3, R1, B means directly from the memory, read the value, add it into the contents of register R1, and then place the result in C. So this is the basic introduction to these different types of architecture. With this much introduction, now we will be talking about some of the merits and demerits of these type of architecture designs. For example, the register type of architecture has the advantage that it is simple and the instruction decoding is corresponding to the fixed length of instruction. It is also simple for code generation and smaller number of clock cycles are required in order to execute the instruction for register mode of operation. Whereas the disadvantage of this architecture are that the higher instruction count, that is the number of instructions in order to write a program, is much larger as compared to register memory type of instructions. However, and the lower density instructions lead to a larger program or say large number of instructions in the program. Whereas the register memory type of design, it has got the advantages of the accessing of the data separately by the load operation, and then the instruction format becomes very, very easy. However, the disadvantage is that the operands are not equivalent, since a source operand is a register and it is destroyed when the destination value is written into the same register. Similarly, the encoding a register and the memory, it requires different number of cycles, and therefore it may have a variable size of the result. Now we will summarize this evolution of the instruction set. Over here on this slide, you can see that it was in 1950 when we had got a design of single accumulator based design. Then in 1953, the Manchester Mark I and IBM 700 series computers were based on the accumulator and register design. Whereas in 1963 to 64, the separation of program models for the implementation was made, and in 1963, high-level language-based computer architectures were developed, whereas in 1964, the concept of a family of computers was introduced. Both these concepts, they were based onto the general purpose register machine, which is further subdivided into two types known as the complex instruction set computer, or the CISC architecture, and it was introduced in the VEX machine, in the Intel 432 machine during the time of 1977 to 80. And the second was the load store type of architecture, which ultimately gave rise to the reduced instruction set computers such as the MIPS or SPARC or IBM RS-6000, etc., and so on. So these are in fact the basic steps through which the instruction set architecture has, different instruction set architectures has evolved. Now, with this much introduction to the instruction set architecture, now I will move on to what are different types of operands which are being used in the computer architecture or in the computer design. Basically, there are three different types of operand which are commonly used, namely the integer type, the single precision floating point, and the character type. Now, these different types of the operands, they can be defined by different sizes of the bit patterns. For example, the characters are specified by as an 8-bit pattern, whereas whenever we have to specify some data, presently a half word is defined as a 16-bit long pattern, whereas a single precision floating point or a word long data is of 32 bits, and a double word long data, which is also known as the double precision floating point, it is of 64 bits in length. Now we will be talking about the categories of the operations of instruction set. The instructions of an operation set can be divided into two distinct classes, that is the operational instructions and support instructions. Almost all computers provide all the operational instructions, whereas different computers provide different support instructions. The most commonly available operational instructions are the arithmetic and logic instructions. These instructions include addition, subtraction, multiplication, division, and logical AND operation, logical OR operation. Whereas the second type of operations are known as the data transfer operations. The data transfer operations are those operations which are used to transfer data either from the memory to the processor, or from the processor to the memory, or from the processor to the I/O devices, or from the I/O devices to the processor. Usually, the load and store instructions are used for data transfer operations from and to the memory. In some machines, the move instructions are also used for this purpose. The third most important type of operations are the control operations. These control operations can be divided into three different types, that is the branch instructions, the jump instructions, and procedure call or return instructions. The support instructions can be considered as of different types of instructions, such as system instructions are those which are used for operating system to handle virtual memory system and similar operations which are dealing with the system management. The floating point instructions are those which are used for arithmetic operations such as addition, multiplication, division, and comparison of the floating point data. The decimal instructions are those instructions which are used to handle the binary coded decimal data, such as the BCD addition, BCD multiplication, or character manipulation. The other type of special support instructions are the string manipulation operations. These string manipulation operations include the string movement from one part of the memory to another part of the memory, the string comparison, and string searching. The last but not the least are the graphic instructions, which deal with the pixels and vertices, and it allows to perform data compression and decompression of the data. So these are basic types of different operational instructions which are used in a computing system. With this much introduction to the data type and types of the instructions which are used in any architecture, now we will be talking about how we can address an operand. Particularly when we are writing an instruction, what are different ways to specify the location of the operand, whether it is available in a register, or it is available in a memory, or it is directly available as part of the instruction. Based on these different places where an operand may be available and how their location can be addressed, we can discuss what are different addressing modes of the operand. Here you can see that I will be talking about the addressing modes by writing it in two different languages known as the assembly language and register transfer language. However, the most commonly used addressing modes include the immediate addressing mode. The immediate addressing mode is one where one of the operand is specified as part of the instruction by the programmer, and it is directly available with the instruction. In assembly language, we can specify this by writing the value of the operand as part of the instruction. As you can see from this slide, where it is written that add R4, comma, hash sign 24 hex. This hash 24 hex represents the immediate value 24 hex, which is one of the operand, and the instruction specifies that the contents of the register R4 will be added into the immediate value, which is 24 hex, and the result will be placed in register R4. This is represented in the register transfer language by saying that the register R4 receives its result from the sum of the contents of the register R4 and an immediate value 24 hex. Here, the data for the instruction is included in the instruction itself. Therefore, it is used where we want to hold the result also in one of the registers. The second addressing mode is known as the register addressing mode, where both the operands are assumed to be available in the registers of the CPU. For example, over here we have written that add R4, comma R3 means we want to add the contents of register R3 to the contents of register R4 and place the result in register R4. And it can be written in the register transfer language as register R4 is receiving its value from as the sum of the contents of register R4 and the register R3. So here both the operands are contained inside the CPU and no memory access is required. The next type of addressing mode is known as the absolute addressing mode. The absolute addressing mode is one where the location of one of the operand in the memory is specified by an absolute address value. For example, as you can see over here, it is written that add R1, 1000 within round brackets. The value within round brackets shows the location of the memory where from the data or the operand is to be obtained. This actually means that we want to add the contents of the memory location 1000 hex to the contents of the register R1 and then place the result in register R1. And you can see it is very clear from how it is written in the register transfer language. That is, the register contents of the register R1 are added to the contents of the memory at location 1000 hex. In this case, hex is always understood that we are writing all addresses or all data in hexadecimal system for convenience of representation. However, in this particular case, the limited address space, which is equal to 2 raised to power the operand field size, which may be 16-bit or which may be 8-bit depending upon size of the register. The next type of addressing mode is very important, and it is commonly used in different type of operations. It is known as the indirect addressing mode. The indirect addressing mode is one where the address of one of the operand is specified indirectly by either the contents of a register or by the contents of a memory location, whose address is specified as part of the instruction. This I will explain to you with the help of this next slide, which you can see over here. The indirect addressing can be register indirect indexed, or register indirect plus displacement, or memory indirect. As I just mentioned, register indirect means that the contents of one of the register shows the address of the memory. This you can see from this next slide. That is, the instruction written as add R4, within parentheses R1, the value within round brackets R1 shows that it is the memory location. However, here I would like to tell you that in assembly language, anything which you enclose in round brackets always mean the location of the memory. Therefore, this particular instruction shows that, as you can see from the register transfer description of this particular instruction, that register R4 is receiving its result from sum of the register R4 plus the memory location, which is specified by the contents of register R1. The word memory, then starting square bracket REG within round bracket R1 means the memory location is whatsoever is the contents of register R1. The second type of indirect addressing is known as indexed indirect addressing. This indexed indirect addressing is usually used for dealing with the array type of data. But you can see over here the address of one of the memory location is specified by the contents of two registers, by the sum of the contents of two registers R1 and R2. One of the register is a base register and the second specifies the index value. Therefore, the location wherefrom the operand is obtained by adding the contents of register R1 and register R2. And this value is transferred into the memory, into the register R4. And it is quite clear from this slide where you can see where this description with the help of register transfer language. The other type of indirect addressing is known as register indirect plus displacement, or simply displacement type of addressing. Here in this particular case, a particular value is specified along with the instruction as which is displacement to the present value or present base value. And the contents of the register R1 in this example specifies the base value, and 100 is the displacement which is added into the contents of the register in order to find the address of the memory location wherefrom one of the operand is to be obtained, and which is added into the contents of register R4, and then the result is made available in register R4. The fourth type of indirect addressing is the memory indirect, and this memory indirect addressing is specified by an @ sign, that is the sign which is usually used by @, and it is used at the assembly language level. As you can see over here, it is ADD R4, comma, @ sign within round brackets R1. This R1 within round brackets after the @ sign actually mean the contents of the memory location at R1 gives the address of the memory wherefrom the operand is to be obtained. This is why in the register transfer level you can see this memory word twice. That is first MEM, after this a square bracket. The square bracket specifies that the contents of the memory address is memory location, which is specified by the address given by the contents of R1 is in fact a location, not the data. The operand is the contents of the memory at a location which is specified by the memory location given by the address specified by the contents of the register. So this gives you 4 different ways of indirect addressing which are usually used in address manipulation or memory addressing system. However, in particular for some special applications, some special instruction or special addressing modes are also used. These addressing modes are known as the auto increment operation, the auto decrement mode, and the scaled mode. The auto increment mode is written as you can see over here in assembly language, it is written as ADD, that is add R1, comma, R2 within square bracket followed by the plus sign. This actually is, during the execution, it performs 2 operations. One operation is performed as a normal indirect addressing mode operation, that is the contents of the register R1 and the contents of the memory location given by the contents of R2, they are added and they are transferred into register R1. But at the same time, after performing this operation, to the contents of the register R2, a value which is equal to D, which is the, in fact, size of the data, that is added into this value, and it gives us the next location or the next value where from the next, during the execution of the next operation, it is to be followed. So this is indeed a method which is used for auto increment purposes. In case of auto decrement operation, the subtraction operation is performed first. That is, D is subtracted first, and then the contents of the memory location are added into the contents of register R1. For example, as you can see from here, ADD R1, comma, R2 within round brackets followed by a minus sign. When it is executed, this operation is executed in two steps. At the first step, from the register R, contents of the register R2, a value equal to D is subtracted. This value is then transferred into the register R2. This now gives us the address which is to be used for data accessing from the memory, and that data is added into the contents of register R1, and the result is placed in R1. The third type of special addressing mode is known as the scaled mode. The scaled mode is one where the operation performed is just like indirect memory addressing. There is first the memory contents, as you can see now from the slide. Register R1 will obtain the data by adding to the contents of register R1 the contents of the memory location, which is in fact equal to 100 bar 100, which is the displacement, plus register R2, that is the contents of the register R2. They specify in fact the value of the location of the memory, and to this value the contents of register R3 are added, which are multiplied by the element size or the displacement size. All these three types of addressing modes are usually used for special operations, particularly during the execution of loop instructions, either forward loop instruction or reverse loop instructions. So this is with this much basic introduction to different addressing modes. Now we will talk about the addressing modes of some of the control flow instructions. As I mentioned in the beginning, the control flow instructions are of three types, that is the branch instructions. Branch instructions are basically the conditional jump instructions. The conditional jump instruction means that when this instruction is executed, then first a particular condition is evaluated. If that condition is satisfied, then the next instruction is obtained from a new address which is needed to be executed if a condition is satisfied. And if the condition is not satisfied, then it will continue in the normal sequence. So this type of conditional branch instruction, it is in fact a sort of displacement instructions, and it is always used with relative to the contents of the program counter. So whatsoever is the present value of the program counter, to this displacement is added, which is in fact specifying the number of instructions which are to be jumped to follow the next sequence. The second type of control instruction is known as a jump instruction. We usually use the word jump for unconditional jump instruction, for unconditional jumping or unconditional branching. This means that this is always, it is also equivalent to say jump always or branch always, that whenever this instruction is executed, it will always transfer the control to a new location. All the control instructions are basically performed through the contents of the program counter. So the jump instruction means a new value is placed in the program counter instead of performing normal value available in the program counter. The third type of control flow instructions are known as the procedure call instructions or procedure return instruction. These are in fact very special purpose jump instructions, where before executing the instruction, the CPU saves the contents of certain registers, including the contents of the program counter, and then the control is transferred to a new location, so that on the completion of a particular execution of a particular procedure, the control transfers to the location wherefrom it was changed to a new procedure, and this operation is known as the return operation. So this means that when we call a procedure, we save the contents of the program counter and some of the internal registers of the CPU. And when we execute a return instruction, this means that the control is transferred back to the previous contents of the program counter, and the original contents of the previous registers, they are returned so that the normal operation continues from its previous location. So these are some special purpose instructions which are used for control operations. Now, with this much introduction about different type of instructions and different control instructions, etc., I will give a brief of what we have talked about today. First of all, we discussed what are the three basic pillars of computer architecture. Then we discussed these pillars are the hardware, software, and the instruction set. Then we talked about the addressing modes of different instructions. These includes the direct addressing, the immediate addressing, the register addressing, indexed addressing, absolute addressing, and so on. And then we talked about the control flow instructions, their addressing. We also talked about different types of architectures which are usually used, such as the stack architecture, the accumulator architecture, and general purpose register architecture. However, next time we will inshallah talk about the encoding of the instructions and how then these encoding lead us to the design of a computing system. So at this stage I will stop here today, and I say you Khuda Hafiz. Thank you very much.